Adolf Hitler led the Nazi regime that caused millions of deaths and a war that altered history. His surname was not always that. He was born as Adolf Schicklgruber, changed his name by his father's decision, and grew up marked by the early death of his mother. He was a volunteer in the First World War, where he received the Iron Cross, although it was later disputed whether he was actually in combat. In prison he wrote Mein Kampf, a text that became mandatory during the Third Reich. He took advantage of a fire to obtain total power, and already as Führer, he controlled the state apparatus. He rejected drugs in public, but his doctor administered opioids and stimulants to him. He accumulated wealth, avoided paying taxes, and was even proposed for the Nobel as a mockery. He ended with a gunshot, surrounded by theories and remains with no clear identity. But beyond politics, war, and propaganda, his regime left traces in objects, systems, and technologies that are still present. What were some of those inventions created under his command that you never imagined? The VG 1-5, the improvised rifle of the final Nazi defense. During the last months of 1944, Germany faced an irreversible military collapse. The defeats in the East and the Allied advance in the West left the regime without sufficient weapons to replace losses at the front. With bombed factories and exhausted resources, the German High Command created a national militia corps called the Volkssturm, made up of older men, young people and workers mobilized in urgency to equip them. The Ministry of Armaments promoted the Primitive Waffen program, a plan designed to manufacture simple and cheap weapons that could be produced with the materials still available. Within that program, several companies were commissioned to develop emergency rifles. Walter presented the VG-1, Spreewak Berlin the VG-2, Steyr the VG-5, and Gustloff Werk the VG 1-5 model, which turned out to be the most advanced of the group. Its creator, Karl Barnitzky, devised a semi-automatic weapon that could be manufactured without complex industrial processes and used components already existing in other production lines. The official designation was Gustloff Volkssturmgewehr, although in its initial phase it received the names MP 507 and MP 508, depending on the type of stock used. The VG 1-5 reached the front at the beginning of 1945. When the war was practically lost for Germany, its purpose was clear: to give the militia a semi-automatic weapon that could use the same intermediate cartridge of 7.92 by 33 mm, the same one used by the STG-44. This ammunition offered good control and effective range in short-distance combat, especially useful in the urban clashes of the final months. Additionally, it used the same magazine of 30 rounds, which helped to simplify logistics amid the chaos at the end of the conflict. Production began in January and ended with the surrender. In May, in total, about 10,000 units were manufactured. The VG 1-5 stood out for its gas-delayed blowback system. Barnitzky had designed a mechanism in which gas extracted from the barrel near the chamber generated pressure opposing the recoil, keeping the bolt closed until the projectile left the barrel. Once the pressure was reduced, the residual force of the casing drove the breech block backward and completed the cycle. This principle would be used years later in some Heckler & Koch weapons, such as the P7 pistol. The weapon had a total length of 885 mm, a barrel of 378 mm, and a weight of 4.6 kilograms. Its muzzle velocity reached about 660 meters per second, with an effective range of approximately 300 meters. The design used only 39 metal parts, of which 12 required machining, 21 could be produced by stamping, and 6 were springs. The reduction of components and the absence of finishes was a condition of the program, which sought to accelerate manufacturing in workshops with non-specialized labor. The sights were fixed iron sights at 100 meters, sufficient for short distances but imprecise at long range. Test reports conducted by the Soviet Union after capturing several examples indicated limited accuracy. At 100 meters, half of the shots impacted within a circle of 10 centimeters in radius, while at 300 meters, the dispersion widened up to 50 centimeters. The bullet drop was noticeable at that distance, forcing the shooter to elevate the sight. However, in the urban combat conditions for which it was intended, that accuracy was acceptable. Its manufacture took place in the Gustloff Werke facilities in Weimar, under direct supervision of the Ministry of Armaments. The last months of production were chaotic. Materials, personnel and transport were lacking, and parts were assembled in emergency shifts. Despite this, the VG-1-5 represented one of the most sophisticated attempts of that last-minute weapons program. The model was delivered primarily to Volkssturm units in defense of cities like Berlin and Breslau, although some batches reached regular divisions of the Wehrmacht. The weapon was not intended for a prolonged, useful life. Its stamped steel structure and riveted parts made it sensitive to wear, but it was cheap and easy to assemble inside. The firing mechanism was built with simple springs and minimal components to guarantee temporary reliability. The weapon lacked a separate pistol grip, and the buttstock was a straight piece of wood of rustic shape. These characteristics differentiated it from the previous Walther and Spreewerk models, which were manually operated and slower in combat. After the surrender, several examples were analyzed by the Allies to study its mechanism. Bunitsky's gas-delayed blowback system was considered a creative solution to the scarcity of materials, and years later its principle was used in more modern designs. The production of the VG-1-5 had no continuity after 1945, but its concept of an economical and semi-automatic weapon became a reference for the post-war period. Historians describe it as the last German rifle manufactured during the conflict, born of industrial collapse and intended for an inexperienced militia. The sonic cannon, the experimental weapon that never worked. In the middle of the war, when the German army was looking for unusual solutions, an engineer named Richard Zippermeyer began working on a project that aimed to convert sound into destructive energy. Technical reports of the time describe it as an attempt to create an acoustic weapon of concentrated pressure, capable of damaging engines or causing internal injuries without using conventional projectiles or explosives. The device, known as the Schallkanone, consisted of a metal structure in the shape of a parabolic tube that concentrated an inflammable mixture of gases. Upon detonating this mixture, a sonic shockwave was generated that expanded outward. The energy produced dispersed in the form of a compressed airburst, but tests showed that the force was quickly lost upon moving away from the point of origin. The tests were carried out between 1943 and 1944 in controlled areas of southern Germany. Post-war Allied records indicate that the effective range was about 200 meters and that the intensity of the sound decreased drastically with distance. In laboratory conditions, the cannon could knock down light sheets and fragile objects, although it did not reach the necessary power to cause real structural damage. The calculations of the technicians from the German Ministry of Armaments showed that the system needed pressures exceeding 150 decibels to be useful in combat. However, the mixture of gas and air could not sustain that pressure for more than a few seconds. The air absorbed the acoustic energy before reaching the target, which made the weapon ineffective beyond a few meters. American documents recovered in 1945 confirmed those results. The physicist Jürgen Altmann, in his study on acoustic weaponry, analyzed the original figures decades later. His conclusions were clear. Sound waves attenuate too quickly in the air and cannot retain the necessary power to inflict bodily or material damage at a distance. According to the compiled data, the energy required to affect a human being at 100 meters would be equivalent to that released by a large explosive, something unfeasible for a portable or short-mounted weapon. Although the cannon did not produce practical effects, it represented one of the first documented attempts to apply acoustic energy for war purposes. In Allied archives, the project is cited as a technical curiosity within the Third Reich's experimental program. The reports catalogued it as a design without tactical value, but highlighted the interest it sparked in the study of frequencies, vibrations, and resonance. The book Sonic Warfare by Steve Goodman describes how sound had already become an instrument of power within the Nazi regime mass concentrations. Loudspeakers in parades and the amplified repetition of speeches created an environment where noise was part of political control. In that context, Zippermeyer's project can be understood as the technical extension of that culture of sound. The intention was not only to generate a weapon, but to exploit the physical and psychological impact of noise as part of the war. Goodman also mentions that other countries, such as Japan and Great Britain, carried out similar trials with low-frequency waves. Without achieving functional results, Germany was the only one to officially incorporate this research into its military program. German engineers tried to amplify the acoustic power through chained combustions in a conical chamber, where each explosion reinforced the previous one. In practice, the tests showed that the main effect was a deafening sound and localized air displacements. After the fall of Germany, the prototypes were transferred to the Office of Scientific Research and Development in the United States, which classified them as research projects without immediate application. Even so, some of the principles observed were later used in studies on non-lethal crowd control devices. Based on high-power sirens and low-frequency generators, Zippermeyer disappeared from the record shortly after the end of the conflict. Reports indicate that he was interrogated and released, and that part of his work was incorporated into the archives of the U.S. Army Air Technical Service. No evidence proves that the weapon was ever tested in combat. Later versions circulated in the press mixed facts with speculation, feeding the idea of an invisible cannon capable of killing with sound. In modern studies on acoustic weaponry, such as Altman's for Science and Global Security, the historical value of that experiment is recognized as a precedent for military acoustic research. Although its results were null, it left a record of a time when the physics of sound was considered a possible tool of war. The BMW R75, the military motorcycle that traveled Europe at war. At the end of the 1930 decade, the German army sought a fast, sturdy, and easy-to-maintain vehicle that could move with the same efficiency on roads and uneven terrain. From that need, the BMW R75 was born, a motorcycle with a sidecar designed to meet the demands of the Heer and the Wehrmacht, becoming one of the most recognizable machines of the Second World War. The project began in 1938, when the Army High Command asked BMW and Zündap to develop a specific model for military use. Adapted civilian models no longer met combat conditions, so the government commissioned a new design with all-wheel drive and reverse gear. The BMW factory in Munich began work on a 745 cubic centimeter boxer engine and a transmission capable of driving both the rear wheel and the sidecar wheel. The first units came out in 1941, and were subjected to tests on different fronts. The BMW R75 demonstrated impeccable traction in mud, snow and sand, and its lockable differential allowed it to overcome slopes impossible for other vehicles. It was equipped with an opposed two-cylinder engine and 26 horsepower, air-cooled. Its gearbox of 4 forward speeds and 1 reverse, along with the possibility of disconnecting the side traction, gave it surprising maneuverability. The chassis was built with reinforced steel tubes and suspensions adjusted to the extra weight of the sidecar. The structure could support loads of up to 500 kilograms between crew, armament and equipment. Its maximum speed reached 95 kilometers per hour, and with its 24-liter fuel tank, it traveled approximately 340 kilometers. Most units mounted the Solex 26mm carburetor, and its 4.5-inch wide tires guaranteed stability on soft terrain. Each motorcycle was assembled following military specifications controlled by the Heereswaffenamt. Soldiers of the panzer divisions and reconnaissance battalions received them as part of the standard equipment. On the Eastern Front, motorized detachments used the R75 for reconnaissance, liaison, and rapid transport of officers or documents. Its agility made it useful in rural areas without paved roads where armored vehicles became stuck. The sidecar carried an integrated drive connected by a cardan shaft, allowing it to move through mud or snow without losing balance. AMG 34 machine gun was usually installed in the front part, operated by the passenger. The standard version also included tools, spare parts, additional fuel, and even spare tires. Some variants were equipped with radio supports or a light mortar, depending on the mission. Starting in 1942, BMW and Zündap unified components under the standardization program, promoted by the Ministry of Armaments to simplify production. The goal was for the parts of both models, the BMW R75 and the Zündap KS 750, to be interchangeable. Although the plan was not completed due to the pressure of the bombings, it allowed the supply of common parts to be maintained until the end of the war. The motorcycle was also used in North Africa, where Africa Corps units used it for patrols, escorts and messaging. Its reliability on sand made it essential for Rommel's operations. In contrast, on the Russian front it was noted for its ability to function in sub-zero temperatures. On many occasions, mechanics improvised thermal protections on the cylinders and used denser oils to withstand the climate. Total production reached around 16,500 units between 1941 and 1944. The main workshops operated in Munich and Eisenach, and in the last months of the war, part of the assembly moved to Austria to avoid air attacks. However, Allied bombings destroyed factories and supply lines, interrupting mass manufacturing. In 1944, the Eisenach plant was occupied by Soviet troops. The original tools and molds for the R75 were sent to the USSR, where they were used to produce the M72, a replica based on the German design. This Soviet model, along with its Chinese version Changjiang 750, prolonged the life of the original project for subsequent decades. Technical documents reveal that the R75 was much more than a simple military motorcycle. It had a system of hydraulic brakes on both rear wheels, a differential that could be manually locked, and a lubrication system capable of withstanding long hours of continuous running. The OHV-type engine, with overhead valves, ensured uniform power even at low speed during the war. These motorcycles were a common part of German convoys. In many photographs, they are seen accompanying supply trucks or light artillery units. They also served for rescue and evacuation missions in bombed areas. Their maintenance was simple and could be performed in the field with basic tools. The standard color was Dunkelgelb, a yellowish tone that replaced the original Wehrmacht grey to adapt to different terrains. The unit insignia, or the Wehrmacht's Black Cross, appeared on the side of the tank. Some later models included a removable dome over the headlight and additional air filters for desert areas. With the surrender of Germany, many R-75s were captured by the Allies and used during the occupation. North American units valued them for their durability and ease of driving. Others were handed over to post-war police forces, where they continued in service for several years. Today, the BMW R75 is a highly sought-after collector's item. Preserved models retain their original chassis numbers and the marks of the German army. Its all-wheel drive and reverse gear system is still admired as a technical advance for its time. Restorers faithfully reproduce the 1942 configurations, maintaining the factory specifications documented in the archives of BMW and the Wehrmacht. Fe-282 Colibri, the world's first combat helicopter. In the hardest years of the Second World War, Germany created a device that seemed ahead of its time, the Flettner Fl 2082 Colibri, the world's first operational helicopter. Its designer, Anton Flettner, had been studying vertical flight for more than a decade when the Reich Air Ministry commissioned him to develop a light machine, capable of taking off in minimal spaces and operating from warships. The model arose from the Fl 265, a prototype with intermeshing rotors that eliminated the need for a tail rotor. The Fl 2082 Phi-2 made its first free flight on October 30, 1941, piloted by Ludwig Hoffmann. Its structure, made of steel tubes covered with fabric, integrated two counter-rotating rotors that guaranteed stability and maneuverability, something unprecedented at the time. In 1940, Flettner set up factories in Johannisthal and Bad Tölz, where the first units with plexiglass cabins were completed in 1942. The German Navy tested the Colibri on the cruiser Köln, verifying its ability to take off and land on deck. Those trials convinced the Naval High Command that the apparatus could serve in maritime reconnaissance and anti-submarine missions. The Colibri used a BMW Brahmo ESH-14 a 7-cylinder engine with 160 horsepower, reached 150 kilometers per hour, and could fly more than 300 kilometers. Its operating ceiling exceeded 3,000 meters, and in case of engine failure, it immediately activated auto-rotation, increasing pilot safety. The Fl 282B2 version, a two-seater, was intended for observation and liaison with artillery. In 1943, the results of its tests motivated an official order for 1,000 units commissioned to BMW, but the Allied bombings destroyed the factories in Munich and Eisenach before it could be completed. Only about 24 came out of production. After the attacks on Berlin, manufacturing was moved to Swidnica in Silesia. In June of 1944, a Colibri piloted by Hans Fusting confronted a Focke-Wulf FW-190 in maneuvers. The fighter could barely keep it in sight. The helicopter moved with such agility at low altitude that it seemed impossible to hit. The tests confirmed its tactical value and its survival capability against enemy aircraft. At the end of that year, the Fl 2082 was used on the Eastern Front as an observation aircraft. Its compact size and stationary flight made it ideal for adjusting artillery fire and detecting Soviet movements. However, the scarcity of materials and the Allied attacks stopped production. In 1945, the workshops were destroyed and the project was interrupted. Only 3 units survived the end of the war. 2 were captured by American troops, identified as V-15 and V-23, and another by the Red Army. Anton Flettner surrendered in Bad Tolz and was later invited to work in the United States, where his intermeshing rotor system influenced later models such as the common HH-43 Husky, the full 2082-01 variant, used by the Kriegsmarine, operated from cruisers in the Baltic and Aegean Seas. A foldable design, A2, also existed, intended to be stored in submarines and assembled on deck. The terrestrial versions B1 and B2 included a rear seat for observers and space for small loads or flares. The Colibri weighed about 760 kilograms empty and supported more than 1,000 with complete equipment. Its metal structure with reinforced wooden rotors allowed it to ascend 1.5 meters per second and fly even with poor visibility. These qualities made it a valuable tool for coastal and rescue missions. After the Allied occupation, almost all the apparatuses were destroyed. However, the technical reports and recovered parts were studied in British, American and Soviet centres. Today, at the Midland Air Museum in Coventry, part of its upper transmission is still preserved, a tangible proof of its advanced design. Considered a milestone of Third Reich engineering, the Flettner Fl 282 Colibri established the technical foundations of modern helicopters. Its system of synchronized rotors, precise control and stability in stationary flight marked a decisive leap in aviation, opening the way for the next generation of vertical takeoff aircraft. Z3 by Zeus, the computer that was born in the heart of the Third Reich. In the late 1930s, in the middle of Nazi Germany, a civil engineer named Konrad Zuse locked himself in his house with an idea that no one understood. He worked alone, surrounded by loose parts, seeking to create a machine that would do the calculations for him. He was not following government orders or developing weapons. He just wanted to free himself from the endless calculations he faced as an engineer. Instead of using decimal numbers, as all calculators did, he decided to work with only 2 values, on and off. Thus was born the first functional binary design in the history of computing. The first model, which he called Z1, he assembled in his parents' living room in Berlin. It was metal, handmade, and frequently failed, but it laid the foundation. Shortly after, he built a test version, more stable, that used electrical relays like those in telephones. He called this the Z2. It served to show the government that his idea could work. The interest was not immediate, but he managed to get a small amount of help from the Air Ministry that was the starting point for what was coming. At the beginning of 1939, already in the middle of the war, Zeus began to build his third model. He did it in Berlin, in a building on Methfessel Street. A few friends helped him. He had no laboratory or large budget, only parts, tools, and a fixed idea, to get his machine to work without errors. 2 years later, in May of 1941, he finished it. He called it Z3. It was capable of executing long calculations automatically, without manual intervention between each step. It did not need to be adjusted or manipulated for each operation. It was programmable. For many, it was the first real computer in history. The Z3 did not use tubes or valves, but relays. It had an internal memory capable of storing more than 60 numbers, each with more than 20 binary positions. Its operations were based on numbers with floating decimals. That gave it more precision than any other machine at that moment. It could be programmed with perforated tapes. Each tape indicated what operations the machine should execute, in what order and with what values. It did not need to be reconfigured. It was given a task and it solved it. All this was happening in Nazi Germany, with the war underway. The Z3 was presented to a reduced group of scientists from the German Aeronautical Research Institute, which was part of the regime's technical apparatus. Only 5 people attended that presentation. There was no press, no one took photos. But the machine worked. It executed complex operations in front of them. It was not an experiment, but a real system. Years later, that same institution would have used it to solve vibration problems in airplane wings. Something that complicated the design of fighters and bombers. Konrad Zuse had created a completely operational machine in the middle of a regime that did not fully understand what it had in its hands. It was not a military priority, and that is why it did not receive more support. Zuse continued working on his machines, but he had to combine it with his service as an engineer in companies linked to the army. It was only thanks to the flexibility of his direct boss, who worked on guidance systems for flying bombs, that he could dedicate part of his time to continue developing his personal project. In December of 1943, during an Allied bombing raid on Berlin, the original Z3 was destroyed. All the photographic documentation was lost. Years later, Konrad Zuse would reconstruct an exact replica, and that version was the one that finally entered museums. But the original disappeared without leaving a visual trace. Only the ideas and blueprints that Zuse had saved survived. The architecture of the Z3 was notable. It clearly separated the memory, the processor, the input system, and the control mechanism. Everything functioned synchronized thanks to a pulse generator. The user entered the data using a console with numerical buttons. The answers were shown with lights. The machine knew how to identify errors such as divisions by zero, undefined results, or out-of-range values. If something went wrong, it stopped and lit a warning light. All this happened without direct supervision. Once started, the machine followed its program until the end. Zuse never managed to get the regime to finance an electronic version of his invention. He proposed substituting the relays with faster systems, but he was told it was not useful for the war. Even so, his work continued to advance. In 1945, he managed to save a later version, the Z4, and took it to the Alps to prevent it from being captured or destroyed. That was the only one that survived the conflict intact. In the 1950s, already in a devastated Germany, he founded his own company and began building new commercial versions. The country was destroyed, but some universities and technical companies became interested in his work. The company grew to have more than 1,000 employees. However, it could not compete with the arrival of large international manufacturers. In 1967, his company was absorbed by Siemens. For a long time, other machines manufactured in the United States were considered the first real computers. Over the years, however, documents and reconstructions demonstrated that the Z3 had been earlier, functional, and programmable. In 1998, an academic team verified that, if all possible paths of a program were executed, the Z3 could be considered universal, capable of simulating any calculation like a modern computer today. Several replicas are preserved. One is in the German Museum in Munich. Another was built full-size by Horst Zuse. The inventor's son educational versions also exist in other museums, where its operation is explained piece by piece. The machine lives on as an example of what can be achieved with ingenuity, even in the worst contexts. The Z3 was not built to launch missiles or decipher enemy codes. However, in the middle of Nazi Germany, and with resources coming from the aeronautical environment, Konrad Zuse managed to show its operation to scientists linked to regime institutions. His story is not limited to a technical achievement. It represents the appearance of a revolutionary technology in a context where no one seemed to pay attention to it. Magnetophon, the German tape that transformed sound recording. At the end of the 19th century, the Danish Valdemar Poulsen had devised an apparatus for recording voice on a wire using magnetic principles. His invention was called the telegraphone, and although it did not succeed commercially, it opened a path that was decades later resumed by an Austro-German engineer named Fritz Fleumer. During the 1920s, Fleumer experimented with ways to apply metal onto paper. After trying bronze powder without good results, in 1927 he replaced it with iron oxide adhered with lacquer. Although the medium was fragile, he managed to record sound on it. In 1928, he patented his idea with the name of sound paper. That recordable paper not only allowed for easy editing, like film reels, but also could be reused. The possibilities were enormous, and the German industry was quickly interested. In 1932, the AEG company obtained the rights to develop a machine that would use it, but because they needed to improve the medium, they turned to AGFA, which would later become BASF. Fleumer suggested changing the paper for a more resistant plastic base, and thus a cellulose acetate tape was born that would revolutionize recordings. The first test model began in 1933 and was baptized as Magnetophon, a compound word that evoked the idea of a magnetic turntable. The portable version was called K1. The official launch of the Magnetophon was planned for 1934 during the Berlin Radio Exhibition. More than 50,000 meters of tape were prepared for the demonstrations, but 2 days before the event, the machine presented faults. AEG decided to postpone the premiere to avoid a failure. The following year, in 1935, the public presentation was made. The machine was sold at a price similar to that of a turntable, and the tape turned out to be much more economical than the recordable wire. By then, the company had perfected the design and reduced the width of the tape to just 6.5 millimeters. That format, called Type C, would remain practically intact for several decades. The impact was immediate. Although the apparatus was not for mass use, it began to be used in radio stations, offices that needed dictaphones, and in some sectors of the army, production remained limited, barely about 100 units per year. But with the start of the war, everything changed. Long propaganda speeches, military recordings, and the needs of the regime caused manufacturing to rise to 500 units annually. At the same time, the audio quality improved. As the technology was perfected, the German government began to keep it secret. Magnetic tape became a resource reserved for the Third Reich elite. Meanwhile, the Allied countries continued recording with more rudimentary methods. Although they knew of the Magnetophon's existence before the conflict, they never paid much attention to it. 78 revolution discs were still the norm, and German advances went unnoticed outside the country. Everything changed at the end of the war. Technicians from the American and British armies inspected factories, radio studios, and laboratories. They soon discovered that Germany had achieved something they did not have: high-fidelity recordings and stereo sound, years before any other country. The patents were confiscated, and Allied companies began to copy the invention. One of the first machines to leave Germany was taken by John T. Mullin, a technician from the American Army's Signal Corps. With the help of the singer Bing Crosby and the engineer Harold Lindsay, they began working on an improved version in California. In 1948, the Ampex company launched its own model onto the market, based on the German design. From there, firms like 3M in the United States, Philips in the Netherlands, and Sony in Japan joined the race. In a few years, magnetic tape became common in broadcasters, studios, and homes. But nobody wanted to remember that this technological advance had been born under the Third Reich. To avoid uncomfortable associations, the official history omitted the Nazi origin of the invention. There was talk of the subsequent advances, of the music industry, of the expansion in cinema and television. But the fact that the first functional tape had been developed in the 1930s in Germany was almost never mentioned. Nor was it said that the first stereo recordings had been achieved there, or that its use was key in the regime's propaganda media. The Magnetophon was silenced even in its own country. Fritz Pfleumer, its creator, did not live to see the international success of his tape. He died in 1945, just as the rest of the world was beginning to copy and improve his technology. Although his name remained outside of industrial tributes, his role was decisive. The shift from rigid recordings to flexible media marked the beginning of a new era. For decades, magnetic tape was the heart of domestic audio, computers, broadcasters, and laboratories. All of that began with an invention patented in 1928, perfected by AEG and BASF, and launched in a Germany that was preparing for war. During the Hitler years, recordings became propaganda weapons. Magnetic tape was not just a technical advance, but a political tool. Speeches were reproduced clearly, could be edited and transmitted without interruption. Control of the message depended on mastery of the technology, an advantage that the Reich effectively exploited. One of the apparatuses used at the front was the Tonschreiber, a version of the Magnetophon adapted for the army. It allowed sound to be recorded and played back in the field, without depending on discs or large installations. Although it was not mass-produced, its existence demonstrates the extent to which the technology was already integrated into the war machine. As the conflict advanced, the Germans sought to maintain the monopoly of these tools. But after the defeat, they could not prevent their invention from changing the world. During the second half of the 20th century, magnetic tape dominated sound. From open reels to compact cassettes, everything arose from that idea born in Berlin in the 1930s. Today, few remember that its origin is linked to the Nazi regime. And although the technology evolved and the materials improved, The basis remained the same: a thin plastic band covered with particles that could be magnetized and erased at will. The legacy of the Magnetophon remained hidden under layers of innovation, but it never disappeared. Pressure suits, the effort to conquer the skies. In the early years of German military aviation, flights at great altitude began to present an obvious physiological obstacle. The lack of atmospheric pressure and low temperatures affected the pilot's performance. It was within the framework of the Third Reich, with the accelerated development of the Luftwaffe, that the urgent need for technical solutions for these extreme environments arose. In that context, German laboratories initiated research to create equipment that would protect aviators at heights exceeding 10,000 meters. The task was left in the hands of doctors and technicians, such as Dr. Wilhelm Pfannenstiel, who had previously worked on altitude physiology studies. The first prototypes were developed in institutes linked to the Air Ministry, combining knowledge of aeronautical medicine with advances in textile materials and mechanical sealing. The idea was to maintain internal body pressure at a tolerable level, while allowing the pilot basic movement. The experimental Model 10-33, also known as the external structure-type pressure suit, used an articulated metallic frame that surrounded the body and allowed compression to be controlled by flexible joints. It was heavy, difficult to wear, and limited mobility, but proved effective in preventing loss of consciousness due to hypoxia. Based on these tests, more refined models were developed, such as the Draeger 191, which incorporated layers of rubber, textile reinforcements, and a less invasive internal structure. The test flights were carried out in hyperbaric chambers and on specially modified aircraft. The results showed that pilots could operate at previously unreachable altitudes without suffering severe effects. However, the complexity of the suit, the time needed to put it on, and its poor adaptability to different sizes made mass use difficult. Despite this, several reconnaissance pilots in the Luftwaffe began to use them regularly during high-altitude missions. In parallel, other German engineering teams worked on pressurization systems for cabins, which could reduce the need for individual suits. However, the technology for sealed cabins advanced slowly, and pressure suits remained the immediate solution. In this context, the Berlin Institute of Aviation Medicine organized tests with new materials and designs. One of the most notable advances was the incorporation of portable oxygen systems connected to the suit, which improved the pilot's autonomy in critical situations. The Hohenfluganzug 10-69 model, the result of that research, managed to combine thermal insulation, internal pressurization, and acceptable mobility. It was evaluated in high-altitude flights over the Eastern Front, where they faced extreme conditions. Medical reports indicated that with this suit, cases of decompression and symptoms related to oxygen loss were reduced. Although it was not intended for direct combat, its use in observation and photography missions allowed vital information to be collected for the German command. The context of the conflict forced the simplification of production. Simpler and less costly versions were created, such as the 10-70 model suit, which reduced the number of mechanical components and prioritized the use of resistant textiles. Although it sacrificed some pressurization efficiency, it could be produced on a larger scale. The industry linked to the war effort adapted assembly lines to manufacture these suits, with quality controls established by the Air Ministry. During the last years of the war, some experimental designs attempted to introduce plastic materials and light alloys to improve comfort. However, the scarcity of resources limited their actual application. In 1944, a commission evaluated the operational use of the pressure suits and concluded that, although useful, their widespread deployment was not feasible in the context of a war of attrition. After Germany's capitulation, the Allies accessed the technical documents and samples of the suits. British and American researchers analyzed their components and manufacturing procedures. Part of that information was integrated into post-war aviation programs. In the United States, institutions such as Wright Field examined the materials and specifications, and some ideas were transferred to the first prototypes of spacesuits. In the United Kingdom, specialists in aviation medicine from the RAF Institute of Aviation Medicine compiled the German data on altitude physiology and adapted several concepts for the training of their own pilots. During the 1950s, the aerospace race benefited indirectly from this research, American agencies resumed the concept of adjustable pressurized suits, perfecting it with new materials and more effective seals. The Mercury project, in its initial phases, considered several of these principles. Although already with domestically developed technology in parallel, the USSR also reviewed some of the recovered German documentation and conducted tests with similar models. Today, the suits used in space stations and extravehicular missions still respect the same basic concept that the Third Reich engineers promoted: protecting the human body in conditions where the atmosphere can no longer do so alone. Although the materials, shapes and functions have evolved radically, the origin of this technology dates back to a Luftwaffe laboratory in the middle of the war. It was not designed to conquer space, but without its first tests, many of the current conquests would never have taken off. Infrared camouflage, the secret paint against thermal vision. In the last years of the Second World War, German laboratories worked silently on a type of technology that sought not strength but invisibility. While the armies fought in broad daylight, Third Reich scientists explored the limits of the infrared spectrum. That research had a clear military purpose: to develop materials that would resist detection by thermal cameras or night vision devices. The idea was for tanks, planes and soldiers to be hidden not only from the eyes, but also from the heat. The Ministry of Armaments and the Luftwaffe's Institute of Physics promoted the first tests with experimental pigments and coatings. It was known that every surface emits thermal radiation based on its temperature, and that this could be detected even in complete darkness. The challenge was to create a layer that would alter that thermal signature. In the technical language of the time, they spoke of reduced emissivity. In practice, it meant designing a paint capable of absorbing and dissipating heat without reflecting it in the infrared range. The first applications focused on armored vehicles. Military reports mentioned trials with coatings on the hull of the Panther tank and other models in production. Engineers from AEG and Zeiss, who had already developed the FG 1250 night vision system, simultaneously proposed a type of thermal camouflage to protect those same machines from detection. The formulas included metallic oxides, carbon, and special resins that reduced the contrast between the hot metal and the environment. Those mixtures were applied as a dense paint, with a rough texture and a greenish or grey tone. In the Wehrmacht laboratories, technicians measured the infrared radiation emitted by different types of paint at different temperatures. The objective was to identify the point at which the surface became almost indistinguishable from the background. When observed with medium-wave detectors, the results were promising. Some compositions managed to reduce the thermal signal by up to 60% compared to bare metal. That meant that a tank could move at night and be much more difficult to locate with detection instruments. The same principles were applied to soldiers' helmets. In a recent study, several German helmet models were examined with modern infrared cameras. The results confirmed that many of the paints used during the war had thermal camouflage properties. The rough finish, the mixture of sand and cement, and the combination of muted tones noticeably reduced reflectance in the infrared spectrum. Even the Reich emblems, painted with metallic pigments, emitted less heat than bare steel. In some cases, the shields and symbols became totally invisible under thermal vision. Contemporary researchers found notable differences between the M35, M40, and M42 models. In helmets manufactured at the end of the conflict, the paint was thicker and contained non-metallic particles that absorbed heat. That detail coincided with the descriptions in the field reports of 1944, which mentioned the introduction of coatings with infrared absorbing properties. They were not simple layers of visual camouflage. They were the result of a systematic policy of thermal concealment. At the same time as these tests, German scientists also developed infrared detectors and viewers. The FG 1250 and Zielgerät 1229 systems, nicknamed Vampir, were used on tanks and rifles during the last months of the conflict. Those apparatuses emitted infrared light invisible to the human eye, reflected by targets and captured by a sensor. They worked with a portable power source and allowed vision in the dark. The problem was that any surface that reflected that radiation could give away their position. For this reason, the same manufacturers designed coatings that absorbed IR light, making targets practically invisible to enemy equipment. The German technical reports captured by the Allies at the end of the war showed diagrams of those coatings. Formulas with micronized iron particles, carbon powder, and silica compounds were described. The key was to control the reflection index in the 3 to 5 micron range, which corresponded to the sensitive band of the detectors. Surfaces painted with those mixtures produced a more diffuse thermal signal, reducing the contrast against the natural environment. Thus was born what would later be called passive thermal camouflage. After the surrender of Germany, the Allied teams seized the archives of the Institute of Physics and the AEG and Zeiss factories. The technical documents were sent to the United States and the United Kingdom. In 1947, several laboratories of the U.S. Naval Research Laboratory analyzed the formulas and replicated the experiments. The conclusions coincided with the original reports. Paint applied to hot metals could reduce thermal detection between 40 and 70%, depending on the type of pigment and the thickness of the layer. During the 1950 decade, the knowledge obtained from those Nazi projects served as a basis for infrared camouflage programs in the Cold War. The Handbook of Military Infrared Technology, published in 1965, documented the optical properties of thermal coatings and their relationship with reflectivity at different wavelengths. Although the text focused on American developments, it acknowledged that many of the theoretical bases came from European research during the war. The sections dedicated to surface emissivity, thermal transfer, and absorption by mineral pigments reproduced data derived from the original Luftwaffe studies in parallel. The CYA compiled reports on Soviet programs that had resumed the same principles. One of those declassified documents described experiments with infrared paints designed to coat vehicles, warehouses, and equipment in combat conditions. The Soviets had analyzed the German formulas captured in Eastern Europe and adapted their own compounds. The materials used included magnesium silicates and titanium oxide pigments, which offered low emissivity in the thermal range. According to the report, the difference between the actual temperature of the object and the temperature perceived by IR sensors could exceed 20 degrees. Celsius later developments also incorporated the concept of dynamic camouflage, in which surfaces were heated or cooled in a controlled manner to match the ambient temperature. Although those experiments were already carried out in the post-war period, the conceptual basis came directly from the German effort to master infrared radiation. The principle was always the same: to alter the way heat is emitted or reflected to deceive the electronic eye as much as the human one. The technical manuals of the 1965 explained that infrared paint did not function as a mirror or a barrier, but as an absorbent layer that converted thermal energy into less detectable radiation. The selection of pigments was crucial. The traditional green and brown tones of visual camouflage were ineffective in the thermal spectrum, while compounds based on carbon and metallic oxides offered a much better response. That finding, recorded by the Nazi scientists in the last months of the war, was still valid 2 decades later. In recent studies, European researchers have examined fragments of German equipment from the Second World War using high-resolution thermal cameras. The tests confirmed that the German camouflage paints had an atypical infrared response. Some surfaces absorbed up to 90% of the incident radiation, becoming almost invisible to modern detectors. The results coincided with the descriptions in the Handbook of Military Infrared Technology and the CIA archives, demonstrating that the Third Reich's advances in thermal camouflage were real and measurable. The legacy of that research extended silently. What began as a desperate attempt to hide tanks and soldiers became the basis of modern camouflage technology. In the 1970s, NATO armies incorporated IR coatings into uniforms, helmets, and vehicles. The microscopic structure of the paints evolved, but the principle remained the same as the German engineers had tested 30 years earlier. Today, the armed forces of different countries use advanced thermal concealment systems based on the same physical laws discovered during the Second World War. Multi-layer uniforms and heat-absorbing paints derive directly from that research initiated by the Luftwaffe and the Wehrmacht. What was then a secret project intended to confuse primitive detectors became an entire branch of modern military science. And although the Third Reich disappeared decades ago, its work in the invisible spectrum of heat left a trace that is still projected onto every vehicle, airplane or soldier trying to hide from the electronic eye of the 21st century. Submersible drones guided submarines and torpedoes ahead of their time. In 1943, when the war in the Atlantic began to become critical for Germany, the Kriegsmarine sought alternatives to Allied dominance at sea. Conventional submarines were increasingly vulnerable to radar and sonar, and losses were mounting. In response, the development of smaller, quieter and harder-to-detect units was promoted. That idea gave rise to mini-submarines and a new generation of remote-controlled torpedoes that would mark the beginning of the era of unmanned underwater vehicles. The project was supervised by the Mein Kampf, a special division created for operations with light vessels. Its technicians and divers worked in collaboration with AEG engineers and shipyards like Germania Werft, who were responsible for designing prototypes capable of transporting torpedoes over short distances and returning to port. The inspiration came from British attacks with manned torpedoes in the Mediterranean, but the Germans intended to go further, replacing direct control with electrical and remote guidance systems. The first operational model was the Molch, a 10-meter-long, one-man submarine propelled by electric motors. It carried 2 externally mounted G7E torpedoes and could reach 6 knots submerged. Its design was simple, but its reduced range made it impractical. Even so, hundreds of units were produced between 1944 and 1945. The first missions were carried out in Norway and the North Sea. With limited results, many were sunk before reaching their targets, although they served as a basis for later, more effective versions. From that experience, the Hecht was developed, conceived as both a manned torpedo and a training vehicle. It was faster, had more precise controls, and could operate in low visibility conditions. In parallel, the Seehund model emerged, considered the most advanced of the German mini-submarines. With capacity for 2 crew members, it weighed 17 tons and was equipped with diesel-electric engines that allowed it to travel more than 250 nautical miles. It could submerge to 30 meters and launch 2 G7 ET-3C torpedoes, the same ones used by U-boats. Its small size and low acoustic signature made it almost undetectable to Allied systems. The Seehund proved its effectiveness in the winter of 1944-45, when several units attacked British convoys in the English Channel. During those months, more than 100 sorties were recorded, with dozens of vessels damaged or sunk. Although official figures were difficult to confirm, Allied reports acknowledged that the small submarine represented a real threat. Its simple structure, combined with non-magnetic materials, allowed it to go unnoticed by proximity mines and field detectors. In several cases, it managed to return to base after completing the mission, which was unusual in that type of operation. While the mini-submarines were being tested in combat, another group of engineers was working on systems that did not require a crew. The result was the development of guided torpedoes, underwater projectiles that could be steered toward their target during the run. Among them, the Zaunkönig and the Falk, designed in the G7E laboratories, stood out. These models used acoustic sensors that detected the noise of enemy propellers and automatically adjusted their course. The principle was simple: an explosive warhead, a propulsion system, and a mechanism that followed the sound of the target. The operator only needed to launch it from a certain distance, and the torpedo did the rest. The Zaunkönig, also known as T5, was the world's first operational acoustic torpedo. It was tested in 1943 and was successfully used against Allied destroyers. Its results led the British to develop sonic countermeasures, such as the Foxer device, which generated artificial noise to confuse the sensor. Even so, the psychological impact was enormous. For the first time, an underwater weapon could autonomously seek its prey. That innovation laid the foundations for modern guidance systems and marked the beginning of the concept of mechanical intelligence applied to naval combat. In parallel, German technicians experimented with wire-controlled torpedoes. These apparatuses could be steered manually from the launching submarine via an electrical connection. They were tested on the G7 ES Lerche model, although their use in combat was scarce due to the cable's fragility and limited maneuverability. However, the principle would later be resumed by post-war naval engineering, especially in the remote-controlled torpedoes used by NATO in the 1960s. Documents captured by the Allies after the surrender revealed that Germany had simultaneously developed several prototypes of unmanned mini-submarines. One of them, called the Neger, consisted of a modified torpedo with a transparent cockpit on top. Inside, the pilot controlled the course and released a second torpedo upon approaching the target. It was a risky design, as it lacked an escape system and had hardly any instruments. Many operators died in the missions. Despite this, the Nazis produced hundreds of units and deployed them in Normandy and Anzio. At the end of 1944, an improved version called Marder appeared, with capability for partial immersion. It incorporated ballast tanks and a ventilation system that allowed it to submerge briefly before the attack. These weapons were difficult to detect and could approach enemy vessels in the dark. They were mainly used to attack anchored ships or those in coastal transit. Although their operational results were limited, their technical concept anticipated future remotely controlled underwater vehicles. The Mein Kampf Verband, responsible for these missions, also formed units of divers armed with magnetic explosives. They operated alongside the mini-submarines, coordinating combined attacks against ports and anchorages. Their training included the use of Delphin-type human torpedoes and remote-controlled charges that could be attached to the hulls of ships. In many respects, those tactics were a mixture of innovation and desperation. Each new model arose from the need to inflict damage with the remaining resources. The Allied technical reports prepared after 1945 highlighted the sophistication of some of those systems. The acoustic torpedoes, the wire-guided models, and the midget submarines demonstrated an advanced level of development for the time. In the following decade, the United States and the Soviet Union studied the German designs and adopted several of their principles. The concept of the mini-submarine, efficient and low cost, was transformed into an ideal tool for reconnaissance and sabotage missions. As technology advanced, the electrical systems, acoustic sensors, and automatic controls evolved toward modern underwater robotics. The Nazi remote-controlled torpedoes, designed to follow a sound or a predetermined course, were the first examples of weapons capable of thinking about their trajectory. The mini-submarines, small and autonomous, anticipated the concept of the unmanned vehicle that is used today for exploration, rescue, or electronic warfare. What began as a desperate attempt to regain control of the Atlantic ended up creating a new type of weapon. Advanced prosthetics, Nazi technology to rebuild mutilated bodies. When Germany entered the war, the regime knew that the human cost would be enormous. Military hospitals soon filled with wounded, amputated, and disfigured soldiers from modern artillery. As the conflict progressed, the number of mutilated exceeded all forecasts. In that context, a systematic effort arose to develop more efficient prosthetics, capable of restoring functionality to veterans. That search not only responded to medical reasons but also to a political purpose, to maintain the image of the combatant as useful to the nation. The National Socialist system organized the care of the wounded through the National Sozialistische Kriegsopferversorgung, NSKOVA, founded in 1933 and integrated directly into the party structure. Its task was to attend to frontline veterans and war wounded, offering rehabilitation, employment, and orthopedic devices. Under its administration, specialized hospitals, mechanical workshops, and readjustment centers were built where amputees learned to handle functional prosthetics. The organization depended on state funds, and its staff was composed of party members and affiliated doctors. In parallel, German industry began producing devices with lighter materials and more precise designs. One of the leading companies was Otto Bock Orthopädische Industrie, founded in 1919 in Königssee. Its founder, Otto Bock, and his successor, Max Noether, were fully integrated into the economic system of the Third Reich. The company manufactured metal joints, mechanical arms, and modular legs intended for veterans of the Eastern and Western fronts. Part of their workforce came from forced laborers, a common practice in German military industry. Despite this, their technical results marked a significant advance compared to previous models. The first prototypes incorporated multiple articulation systems that allowed for more natural movements. Some prosthetics included spring or cable mechanisms that imitated the action of muscles. Workshops were set up in hospitals in Berlin and Munich, where the wounded learned to manufacture and adjust their own devices under the supervision of the NSKOV, which sought to adapt each prosthesis to the veteran's future work function. The goal was to reintegrate the mutilated into industrial work and keep them as an active part of the national effort. Between 1934 and 1944, a notable increase in patents related to prosthetics and orthopedic systems was registered. A later study by the National Bureau of Economic Research showed that Germany concentrated a significant part of the wartime medical innovations in this field, with improvements in fitting, joints, and low-density metallic materials. Although many of those innovations were born out of wartime necessity, they also responded to the regime's interest in projecting an image of technical efficiency and scientific superiority. The factories that produced prosthetics operated under state control. The Ministry of Armaments, led by Albert Speer, coordinated the distribution of strategic materials such as aluminum and rubber. The priority was to attend to combatants considered useful, that is, those who could rejoin the workforce or instructional tasks. Veterans with severe disabilities were sent to long-term institutions where prosthetics served a more symbolic than practical function. These technologies were presented in public exhibitions as proof of supposed German scientific superiority. Medical archives of the time mention mechanical arms controlled by shoulder movements and devices that allowed holding light tools or weapons made of anodized aluminum or tempered steel. They required high technical precision. Engineers from Otterbock and the Reichsinstitute for Orthopädie experimented with different couplings to improve mobility. In some cases, interchangeable connections were used that allowed the prosthesis to be adapted for various uses, from agricultural tasks to operating machinery. The use of advanced prosthetics also served a propaganda function. Newsreels showed amputee soldiers returning to work or marching with their new devices, reinforcing the idea of sacrifice and recovery under Hitler's leadership. In party speeches, the mutilated veteran was exalted as a symbol of resistance. Orthopedic technology thus became an ideological instrument that united medicine and propaganda. As the war dragged on, production was decentralized. The workshops in Berlin and Hanover were moved to rural areas to avoid the bombings. Technicians incorporated synthetic plastics, such as bakelite, to supply scarce materials, and developed faster molding methods. Each prosthesis was numbered and registered by the medical authorities. By 1944, thousands of veterans were equipped with modular, easy-to-repair devices. The work of Otterbock during the Third Reich left an ambiguous legacy. On the one hand, it contributed to the technical progress of orthopedics. On the other, it was part of the Nazi economic system and employed forced labor. After 1945, Max Nader maintained control of the company and collaborated with the occupation forces to continue production for civilian purposes. Its designs served as the basis for post-war prosthetics in West Germany and were adopted in Allied hospitals. Studies on the evolution of electric prosthetics recognize that several modern solutions derive from those experiences. Myoelectric arms and joints controlled by electrical impulses have their origin in the experiments with tension cables and springs of that time. Although the Nazis did not manage to create automated devices, they laid the foundations for applied biomechanics. In the reconstruction of post-war Germany, many of those patents were resumed by the same companies that had worked for the regime. In the archives of the Orthotics and Prosthetics Library, tests with electrically powered prosthetics in the 1944s are described. German engineers explored the use of small motors to move artificial fingers and wrists. These projects were not completed before the end of the war, but they inspired the research programs of the United States and the United Kingdom in the 1950s. The technology created for the Reich's veterans ended up influencing the design of modern functional prosthetics. The end of the conflict left a huge number of wounded and amputees across Europe. Many German veterans, beneficiaries of the prosthetics produced under the NSKOV, were integrated into the post-war health system. The factories that survived continued operating under civil administration. The technical advances achieved during the Third Reich, such as the use of light materials, precise joints and quick-release fastening systems, marked the origin of modern orthopedics and served as a basis for its development in subsequent years.